Second and third laws of thermodynamics. Second law in terms of heat flow. The second law of thermodynamics has many different, seemingly unrelated formulations that can be applied both to physics and everyday life. One formulation of this law is with the relationship of heat flow. It states that heat naturally flows from a hotter object to a cooler object and will never flow in the opposite direction. Heat will not move from a cooler object to a hotter one. Basically, without an external force, hot objects will become cooler and cold objects will become warmer. An example of this in everyday life is when you take food out of an oven. The food begins cooling to the temperature of the room. The food does not magically warm up after it is taken out of the oven into a cooler environment. Likewise, cold ice cream melts when you take it out of the freezer because the ice cream is becoming warmer to match the temperature of its environment. This law also explains that when you take a warm soda and put it into a cooler full of ice, the cold of the ice does not transfer to the warm soda, but instead the warmth of the soda transfers to the cold of the ice, releasing heat from the soda, making it colder, and adding heat to the ice, causing it to melt. The cold cannot transfer to the hotter object based on the second law of thermodynamics. Second law in terms of entropy. Entropy is the measure of how disordered a system is. The less ordered a system is, the higher its entropy. The second law states that ordered systems are liable to fall into disorder, but disordered systems do not order themselves spontaneously. Much like the relationship to heat flow, the amount of order in a system only flows one way, towards more disorder. An outside force must be applied to cause the system to become more ordered. An example of this would be if you had a bowl with two mounds of ingredients, one pile of salt and one pile of pepper, both separate stacks but in the same bowl. This simulates an ordered system. Now if you take the ingredients and mix them together, the salt and pepper combine into one mixture. This simulates a disordered system. The law is apparent because no matter how much you mix the ingredients, they will never return to their ordered way, two separate piles. This law can also be applied in a broader sense by applying it to life and the universe in general. As explained by Morgan Freeman and Michio Kaku, the second law of thermodynamics explains why we age and why we die.
Michio Kaku, a theoretical physicist at City College of New York, is fascinated with the big questions in science, like whether the laws of physics require that all living things die.
One of the iron laws of physics is the second law of thermodynamics, which says that everything rusts, everything decays, falls apart. We're all made out of atoms, and these atoms in turn obey the second law of thermodynamics.
Anything and everything in the universe has the tendency to go from order to disorder. And once the damage is done, it's extremely difficult to reverse things and unmix them. It's a process known as entropy.
If I mix coffee, I realize that when I put cream into coffee, I increase entropy, I increase disorder. In fact, to see this milk jump out and reform in this cup is such a preposterous event that you would have to wait longer than the lifetime of the universe to see it happen.
The second law of thermodynamics is an unremitting force. Nothing is immune to the power of entropy, not even the cells in our body.
And that's why we age. In fact, that's why we die.
Second law in terms of heat engine. A heat engine is a system that converts heat or thermal energy into mechanical energy. This occurs by bringing a substance from a lower state temperature to a higher temperature. Steam engines, diesel engines, and a gasoline engine in a car are all heat engines. The second law of thermodynamics states that no machine or system can work 100% efficiency because they lose some energy and heat. Basically, no matter how expensive a car you have or how fuel efficient it claims to be, it will never be 100% efficient. Some of the energy that could be used to power the system will be lost in the form of heat. This can be explained using the Carnot heat engine. The Carnot heat engine helped develop the concept of entropy. This engine is a hypothetical model in which a thermodynamic cycle occurs. This means that the system is taken through a series of different states and finally returned to its initial state. Through this process, the system performs work on its surrounding, acting as a heat engine. The heat transfers energy from a warm region to a cool region of space and converts the energy created into mechanical energy. This model formed the basis of the idea that no machine can work at 100% efficiency because no real heat engine will be able to be more efficient than this theoretical engine, which isn't even 100% efficient. The third law. The third law of thermodynamics states that all molecular movement stops at a temperature called absolute zero. This occurs at 0 Kelvin or negative 273 degrees Celsius. Since temperature is the measure of molecular movement, it makes sense that there is a limit to temperature, called absolute zero. Since it is not possible to have negative molecular movement, there can be no temperature less than 0 Kelvin. Absolute zero, however, cannot be reached. It is a limit that as you approach, its entropy of the object approaches a constant. It is not possible to remove that last little amount of heat in the system to cause it to reach absolute zero. The idea of absolute zero in calculations is useful because it gives a perspective point in which the calculations can be based off of. Third law in relation to crystals. The entropy of a perfect crystal at 0 Kelvin is 0. This is useful because, although it is not possible to achieve a perfect crystal, it allows other values of entropy in crystals at other temperatures to be calculated based on this perspective point. As you can see, on the left is a perfect crystal, which is only theoretical, and on the right is a crystal that you'd see, such as a diamond, where it's not all perfectly aligned. Conclusion. Although most people don't think about the way food cools when you take it out of the oven instead of heating up, the second and third laws of thermodynamics are very important to explaining the physics of systems. These laws explain why certain phenomena cannot occur and that there is a temperature, although yet not possible to reach, in which all molecular movement stops. Next time you are sitting outside with an ice cream cone, think about these laws and how you wish they weren't true so your ice cream wouldn't melt. Here's my works cited. Thanks, guys.